Hello everyone, this is Uday and welcome to Uday Lectures. In this video, we will discuss how we can perform insertion operation in AVL tree. In last video, we have seen what AVL tree is and the properties of AVL tree and what different rotation operations we make use in AVL tree to balance the AVL tree and how we get to know that whether tree is balanced or not balanced with the help of balance factor formula. If you missed that video, please do watch that video first and so that you will understand this AVL tree operations clearly. And if you don't understand balance factor, what is balance factor and the properties of AVL tree, and more importantly, the rotation operations. And if you don't understand them, when to perform and where to perform and how to perform, it is difficult for you to understand how we perform insertion operation. So do watch that video. And it is really important to understand binary search tree insertion operation to understand AVL tree insertion operation, because we will be following the same steps of binary search tree insertion operation in AVL tree insertion operation, because AVL tree is an extended version of binary search tree, and that is why we will be following the similar steps of binary search tree for performing AVL tree insertion. But that is the only step. It is not all the steps in AVL tree insertion operation. Okay, I have already made a video for binary search tree insertion operation and also binary search tree properties and deletion operation. Do watch those videos. If you don't watch those videos, if you don't understand what binary search tree insertion operation, you will not understand this video also clearly. Okay, do watch that video. You will be notified with that video link also. Do watch that video. I'll also put that in the description section, the link for that particular video, so that you will be able to access that video and understand binary search tree clearly before getting into AVL tree insertion. Okay, now let us dive into this AVL tree insertion operation. So AVL tree insertion operation is performed similar to binary search tree insertion operation. So in binary search tree, we insert a new node as leaf node itself. And here also we will insert a new node as child of leaf node. We cannot insert that as internal node or root node. Okay. And after we perform the insertion operation by following the rules of binary search tree, the important steps are this to be performed in AVL tree insertion. So the first step is that you compute balance factors for all the nodes after inserting a new node. And after you calculate balance factors, we have to check if any of the nodes are unbalanced. If any of the nodes are unbalanced, now we have to perform required rotation operations until the tree is balanced. Now, what different rotation operations there are? I already made a video on AVL tree rotation operations. Do watch that video to understand how rotation operations work and when it is to be taken or when it is to be performed. All right. So these are all the steps that we follow for AVL tree insertion operation. The steps are very simple. You insert a new node similar to binary search tree and following the rules of binary search tree. After you perform insertion, now you have to compute the balance factors. After computing the balance factors, now we will end up performing rotation operations if the tree is not balanced. So these are all the only steps. Now we will dive into your example problem. We will construct a AVL tree by following the insertion operation by taking some numbers. All right. So let us just dive into that. Right now I have taken some list of numbers. So this is the simplest example that I have constructed, wherein we will end up with all the possible rotations there are in AVL tree, like left rotation, right rotation, left right rotation, and right left rotation. And this particular example problem comprises of all those rotations and which will explain all the situations. So if you consider this problem as example problem in your exams, in attending exams, if an question is asked construct an AVL tree, then go with this particular example, because this example will give you all the rotations and all the different situations, and it will be easy for you to explain them in your exam, right? So if you go with this example, you will be able to answer them very clearly and very impressively, and you will be getting better marks in the exam also. Okay, now let us understand how this problem can be solved. If these numbers were given to you and asked you to construct AVL tree, this is how we will solve them. So first we will go with the first number, which is inserting 70. Okay, And to insert 70, we can insert 70 directly into the tree because 70, the tree is completely empty now. So according to binary search tree, we can make a new element as root node if the tree is completely empty. So for this you have to understand binary search tree. I'm telling you again, do understand binary search tree first clearly, and only then you will be able to understand AVL tree. Okay. If you don't know what binary search tree and how we can construct a binary search tree, do watch a video which I have made already for binary search tree. Okay. Now, after inserting 70, now we have to compute the balance factors. So the balance factors for this will be 0 because height of left subtree is 0 and height of right subtree is also 0. Now let us get into the next number, which is inserting 52. Okay. And now where do we insert 52? To the left of 70. To the left of 70, which is 52. Okay. Now we have to compute the balance factors. Balance factor of leaf node will be 0 and balance factor of this node will be 1 minus 0 because left subtree height is 1 and right subtree is 0. So it is 1. Still the balance factors are within the range of 0 and 1. So now we don't have to worry about rotation operations. Now we'll insert the next node, which is inserting 40. Okay. And to insert 40, where do we insert 40? To the left of 52. So to understand these steps, you should be understanding binary search tree, right? And that is why I said understanding binary search tree is really important. So after we insert 40, now we should compute the balance factors. Let us compute them. So leaf node balance factor will be 0. Now 52 is having one left child, so height of it is 1. And 70 is having two left childs but no right child, so the balance factor for this will be 2. Now if you see, the balance factors are not within the range of, what is the valid range of balance factors? So it is -1, 0 and 1. Okay. So the properties of AVL tree also, I made a video. You can also watch that video to understand different rotations and what is the balance factor and all them. Okay. So now since the balance factor of this node is impacted, now we will end up with performing rotation. Now what rotation should we perform? We should be performing something called a right rotation. Okay. Why right rotation? I already explained that in the video. You can also watch that video to understand that. Okay. So in right rotation, so the parent node becomes the root node, and then the present root node will be sent to the right side. That is why we call that as right rotation. Now we will see how the tree would change into. So 52 becomes our parent node now, and 70 is pushed to the right side, and 40 stays in the same position. So now the rotation is complete. So since the rotation is completed, now we have to calculate the balance factors. So the balance factors for this particular leaf nodes are zeros. And for this it is left subtree height is 1 and right subtree height is 1. So 1 minus 1 becomes 0. Now the balance factors are within the range. So now the tree is balanced. Now we don't have to worry about anything. Now we will insert the next node, which is 91. Okay. So inserting 91, right? I'm sorry. Let me just get that straight. So the present tree is this. So where we have 52, 40 and 70. So the node that we would like to insert now is 91. 91 goes into this side. Okay, because according to the rules of binary search tree, after insertion, now we have to perform the balance factor computation. So the balance factors for this leaf nodes will be 0, and for this 70 it is left height is 0 and right height is 1. So it is 0 minus 1, so we will end up with -1. And for this it is 1 minus 2, so which is -1. So still the balance factors are within the range of -1, 0 and +1. So now we are done with inserting 91 also. Let us insert the next node. Right. So now we have to perform a rotation. And what rotation should we perform now? We will end up performing a left rotation. When we insert a right child to the right subtree, we will end up in left rotation. And this I've already explained in the previous video. If you missed that video, please do watch that video, alright? So now, in this left rotation, the left rotation is performed only between the parent and the grandparent. Do remember, in RL rotation and LR rotation, the rotations are performed first between the child and the parent, and then between the parent and the grandparent. But where in left rotation and right rotation, the rotation is performed only once, and that is between parent and the grandparent. So here we are trying to push 85 to the left side, and that is why we call this as left rotation. Okay, let me just finish this rotation. 52 stays as it is, 40 also stays as it is, 60 also stays as it is. Now we are trying to move 85 to the left side. So what will be the root node now? 91. And 85 becomes our left node. 92 becomes our right node. Okay. Now we have completed the rotation. Now we will compute the balance factors. Zeros for this, leaf nodes. And for this it is 1 minus 1, which is 0. For this also 1 minus 1, 0. For this also 2 minus 2, which is 0. Okay. Wonderful. Now the balance factors for all the nodes became zeros. Right. Now we will insert the next node, which is 30. Okay, so we will try and insert 30. Inserting 30. Okay, so to insert 30, let me consider the present tree, which is 70. Okay, let me just change the pen. 70, 52, 40, and then 60, and then I have 91 in the right side, 85, and then 92. Okay, let me just scroll a little more. Okay, I'm trying to insert 30. So 30 goes here according to the binary search tree properties or rules. Now after inserting 30, we have to compute the balance factors. 0 for leaf nodes. Okay, 0 for this. And what about this? It is 1, because 1 minus 0. For 52 it is 2 minus 1, which is 1. For this it is 3 minus 2, which is 1. Okay, now the balance factors are within the range of 0, 1 and minus 1. So now we don't have to worry about anything. We can insert the new node now. So what is the next element? 35. Okay, which is 35. I'm trying to insert 35 now. Okay, so to insert 35, I have to consider the present tree, which is 70, 52, 40 and 30, and 35 goes here. Okay, and then 60. Okay, so my focus is to get all the possible rotations and different situations in this example itself. That is why I'm inserting this nodes in this particular way. Okay, so if you look closely, all the rotations are performed, and now we are trying to perform one more rotation. Now this insertion will allow us, or will get us in a rotation operation for sure. All right, let us calculate the balance factors first. 0 for this, minus 1 for this, and it is 2, because left subtree height is 2, and for this it is 1 2 3, 3 minus 1, which is 2, and for this it is 1 2 3 4, 4 minus 2, which is 2. For this it is 0 0 and 0. Now if you see, 3 nodes are impacted because of inserting one node, and first we have to go in bottom up approach, so we will end up performing rotation between this. Okay, and what type of rotation this is? This is in this structure, so which is left and right. Okay, so we are trying to perform left right rotation. Now in left right rotation, first we have to perform left rotation, wherein getting this 35 to the left side or 30 to the left side by making 35, and then we should perform a right rotation. Okay, so first we will perform the left rotation because it is a combinational rotation. First we will be performing a left rotation, and then we will be performing a right rotation. Okay, so our goal is to get them into this particular structure, and here it is going to change into this structure. Okay, now we will construct the left rotation, or consider the left rotation. 70, 52 and 40 stays as it is because left rotation is performed in this case between child and the parent node, and 35 becomes our root node and pushing 30 to the left side. Okay, and now we have 91 as it is, 92 and then 85. right? Now we missed one more node here, which is 60. All right, we should perform one more rotation, only then we should be calculating the balance factors. So now we have to perform the rotation between 35 and 40. And what rotation is that? Right rotation. Now 70 comes here, 52 goes here, and 60 is connected as it is. And now 35 becomes our parent node by pushing 40 to the right side, and 30 stays left as it is. 91, 92, and then 85, right? This is 92. So now we are completed both the rotations. So now we have to compute the balance factors, zeros for all this, zeros for leaf nodes, 0 for this also because 1 minus 1. For this it is 2 minus 1, which is 1. For this it is 1, 2, 3, 3 minus 2, which is 1. Now the balance factors are within the range of minus 1, 0 and 1. So now we are done with inserting 35. The last element for this example, let us just complete it. Okay, so we have inserted 35 also. Now we will insert 25. Okay, now we are inserting the last element in this example, which is 25. Now we will insert 25 into the tree. And where does 25 go here? 25 will be inserted to the left of 30. Now we will compute the balance factors for them. 0 for this and 1 for this, and it is 2 minus 1, which is 1, and for this it is 0, and for 52 it changes, 3 minus 1, which is 2, and 0 for this, 0 for this, and 2 and zeros for this. All right. Now if you look closely, the balance factor of 52 is impacted because of inserting 25. Now we have to perform a rotation to balance 52. Okay, but now if you look closely, I can either consider 52, 35 and 40 for the rotation, or 52, 35 and 30 for rotation. Now which we should be considering is which is inserted direction, that is where we should be considering for the rotation. Now that 25 is inserted to the left side of 35, that is why we should be considering the left subtree of 35 for the rotation. Now what rotation should be performed? We should be performing right rotation. Right. Now we will see how the tree will change into. So we have 70 as it is, 52 here, and my apologies, not 52, because 52 should be pushed to the right side. That is why we are performing the right rotation. So what happens now? 35 becomes our new parent. And what happens to 52? It is pushed to the right child. And 52 is already having a right child, which is 60. But for 35 also is having a right child, which is 40. Now what should we do? 40 must be connected to 52. And 40 is connected as left child to 52 because 40 is in the left subtree of 52. Right. Now 35 is having a left child, which is 30, and 25 as left of 30. And now 91 is right subtree of 70, 92, and then 85. Now we have completed the rotation. Now we should calculate the balance factors. 0 for this, 1 for this, 2 minus 2 it is 0, 0 for this, 0 and 0 for this, leaf nodes, zeros and zeros, for this also 0 because 1 minus 1, and for this 3 minus 2, which is 1. Now if you see, the balance factors are balanced for all the given nodes. Now we call this as a valid AVL tree. Okay, hope you understood how we constructed a AVL tree for this particular problem. I know that this video is lengthy, and also this problem is very huge, and I have considered this example because here I have all the possible rotations included. So here if you see closely, I have performed right rotation in this case, covered right rotation, and here we are performing right left rotation, covered right left rotation also, and here we have again right left rotation, you have right left rotation again, right? And here we have left rotation, and here we have a LR rotation, which is left right rotation, and here we have right rotation finally. Okay, so here in this example I have covered all the rotations that are there in the AVL tree and different situations you will come across. That is why I have considered this example for making you all understand how insertion operation works in AVL tree. I hope you understood this topic. If you have any doubts, please feel free to mention that in the comment section. And if you're stuck in solving AVL tree problem, or you have any given problem, you're not able to construct an AVL tree for that, mention that in the comment section. I'll make a dedicated video for that example problem also, and I will make sure that is available in the channel. So you can try solving that problem, and you can also understand how to solve those particular kind of problems. And it is really important to understand binary search tree to solve AVL tree problem. I've already made a video for that. Do watch that video if you have if you're not sure how binary search tree work. And it is really important to understand what balance factor, how to find balance factors for the nodes, and what different rotation operations there are in AVL tree and how you perform them, and when and where you perform rotation operations in AVL tree. It is really important to solve the problem in AVL trees. Do watch that video also. I have made a video for rotation operations in AVL tree also for you to understand. Watch those videos before you get into this video. And if you like the content of this video, please do like this video. Share this video with your friends if you feel this video is worth of sharing with your friends. And to watch further content on data structures and different programming languages, I'll be uploading them in my channel. Please do subscribe to this channel so that you will be notified when I upload a new video. Thank you so much. Have a wonderful day ahead. Thank you.